Okay, so today we will close our introductory part of the course, and then we will go to the actual meat with the different methods for doing research in empirical software engineering. Okay, today we will speak about building theories in software engineering, and we will speak about also which are the different strategies for performing empirical studies in software engineering. Last time we saw data collection methods, which is just a part of the whole research process. Okay, today we will see what surrounds which are the strategies that are using also those data collection methods. But first, let's start with more of a philosophical part, let's say, of this course, that is related to how to a general view on how we build the theories in our field. So first of all, what is a theory? A theory is a term that we already used both in this course, and you of course also know yourself, and you use it yourself. But what is exactly? Let's read the slide also in this case. A theory is a statement about the existence of some pattern in the entities that belong to a certain context. So basically the key here is pattern, okay? Every time there is a regularity in the word, or in like in my area of interest, okay, I can build a theory. And the theory is about entities. Entities here is a generic word that can be translated also as observable phenomena, and includes both objects, so static elements, and events, so dynamic elements, and that belong to a certain context. It is important to consider that there are regularities about entities, and they are in a certain context. Why is it important to consider the context? Because the context is the boundary, is the scope of applicability of the theory. For example, I can build a theory that is related to the context of all the people in a certain company, or I can build a theory that is related to all the C developers of the world. So the context, the boundary to which the theory is referred is different. Okay, so remember this thing. Theory is associated to patterns, which and to entities and to specific contexts. Considering this, I can have different levels of sophistication of a theory, and it depends on how much abstract are these entities considered. So how much abstract are the objects and the events that are considered the observable phenomena. Okay, abstract means how far are them from direct measurable observation. So how far are them from things that I can evaluate with numbers somehow. Okay. Here I made three different examples that give you an idea of what is the different what are the different level of sophistication of a theory. So we have low level of sophistication. For example, this is a theory. 90% of faults are found in functions that are longer than 1,000 line of code. Okay. Here you see that this is a theory because it's a pattern. It's some form of regularity in the word, because you can say that 90% of faults is something that happen like for example, in the context of a company, and or in the context of all the C functions. Okay, here come again the context, but still it is a regularity that I'm stating a pattern somehow that I want to frame with this theory. And in this case, it's quite easy to be verified precisely. It can be verified quite precisely because I'm dealing with frequencies and I'm dealing with real objects. Okay, and the measurements that I take are quite are close to the observation. So the lines of code is something that I can count easily. Okay, and once I have given the definition of a fault, also a fault can be identified quite easily. Okay, then I have another level of sophistication that is higher. For example, consider this theory. Requirements defects can be classified into unclarity, incompleteness, and incorrectness. First of all, here I see that I don't have numbers. Okay, And this is the first issue that makes me think that, okay, is already more abstract than the other one. Okay, here I need, first of all, some precise definition of the three classes. So what does unclarity mean? What does incompleteness mean? What does incorrectness mean? Okay, and I have to assess that all the existing defects, okay, all the existing defects in my context always can be linked to one of the classes. So it can be, if I take a random defect, it can be classified in one of these three classes. Either is unclear or incomplete or incorrect. Okay, and not only this, but I have to assess that every person that has to link the defect to one of these classes actually classify the defect in the same way or in similar way. The verification of this theory is much more complicated, okay, with respect to the other case, okay, because I need to introduce all these other definitions and context and evaluation that are less accurate, unavoidably less precise, okay, and then I can have even higher level of sophistication, for example, but still speak about the theory and something that I can assess and evaluate. For example, this case, if the team leader is not self-confident, developers lose trust. First of all, here is not just dealing with something that is referred to an object, a requirement. Okay, it's referred to a quality of a person. So self-confidence, trust. Okay, what is self-confidence? How can I evaluate it? What is trust? How can I estimate this? Okay, verification of this concept that are, you understand, very abstract, much more abstract than the other one that we were speaking about up to now, requires, unavoidably implies that verification of this theory is much more difficult, okay? And especially precise verification of this theory is much more difficult, okay? In software engineering, you find all these different types of theories, okay? In software engineering, you have to consider that you will meet all these different granularities, okay? And this is also the interesting thing, because you deal with different, as I told in the first lecture, you deal with social aspect, technical aspect, human aspect, emotional aspect, but also numeric and software related aspect. Okay. So this was what a theory is. What a theory does. A theory can do this, mainly these 5 things. So it can describe, it can explain, it can predict, it can do explanation and prediction, and it can do, especially in engineering, design and action. So it can also allow to modify the reality. Okay. For description, for when a theory analyze a problem, okay, the product is normally are normally descriptions and conceptualization. So a theory can be a taxonomy and ontology, like the case of the defect types that I gave before. Okay, so that one was a descriptive theory. Okay, the fact that that requirements, defects can be classified according to those different classes. Okay, a theory can also explain, so can allow to identify the motivation for something, and in this case you have to consider the example of the team leader. So the team leader example tells us the motivation why developers tend to lose trust. So it is explained according to the degree of self-confidence of the team leader. Okay, it can predict. So I build a model and I predict how things are in the reality, like in the fault example. So in the example in which I was speaking about the presence of faults that are found in functions that are longer than 1,000 lines of code. So this is a model. If I found a function that is longer than 1,000 lines of code, I can predict that there will be some faults. Explanation and prediction. So I find the model. So I find the model about the for predicting the faults, and I also find the motivation why longer function or functions that are longer than a certain amount of lines are more faulty. Okay. Or I can do also design and action with the theory. Design and action means that I use the information to transform the reality. This is, I don't have the example here, but if you remember in the first lecture, I was giving you an example about testing resources, the one about the developers that if they code at night, they create more bugs and they are more productive, but they are more productive. So the solution was, the solution theory, actually, I called it at that time, the solution theory was to dedicate more testing resources to the code developed at night. Okay, so this is another type of theory. So it's a theory, is a solution theory oriented to design and action. So remember that the theory can do all these type of things, and the example are quite clarifying, I guess. Now we've seen what is a theory, what a theory does, and now we will see what are the elements. Okay. The elements are, if you want to remember them, you can remember also the typical questions to which they refer. So, first of all, what? First question is what, and let's read here. What are the entities in terms of which a theory offers description, explanation, prediction, and prescription? These are the constructs of the theory. So the the basic entities, okay, that form the theory are called constructs. We'll use this term later on, okay? Then there is a question how, that is referred to how these constructs are related, okay? What are the relationship? And the second thing that builds a theory are the propositions, so statements about the interaction between constructs. By constructs, I will give you example later on. We intend basically, if you are confident with the entity relationship diagram, all the entities, so it can be objects but also attributes. Okay, the constructs, we will see some example later on. Okay, so we have constructs, prepositions, and the preposition can also lead to prediction, of course, but here just remember construct and preposition. And there is a third question that is why a certain relationship holds. So this is what gives theory explanatory power. We will see this in the next slides. And in the end, I have several other questions, which are where, when, and for whom, that are the scope condition, that identify the circumstances in which the theory is applicable. So these additional questions are the context. So constructs, propositions, the answer to the question why, motivation for which a certain relationship holds, so the explanation, okay, and scope condition. Construct, prediction, explanation, and scope condition. We will see example of these elements very soon. So constructs. Constructs as the elements. Okay. Here are examples to give you a flavor of what we intend here. UML-based development methods. If you don't know what is UML, you can check internet, but it's basically a set of diagrams that are oriented to design software mostly for object-oriented design. Okay, and the development method based on UML consists in using this diagram to guide the development of software. So for creating the software design and architecture that allows them to develop that is the blueprint for developing the software. Okay, but also cost, communication, design, documentation, testability. So these are all concepts. Okay, all the constructs are concepts that are relevant for my research and are relevant for my theory. Okay, Proposition, how the constructs interact. For example, here there is a list of proposition. This is a P4 is a proposition. For example, the use of a UML-based development method positively affects documentation. So using this method, you have a better documentation. This is a proposition because it relates UML development method with another construct which is documentation. Okay. Explanation. Explanation is the third component and explain why this relationship P4 hold. The documentation is more complete, more consistent because there is more traceability between models and code. It means that I can trace the blueprints or the diagrams with the actual code. More understandable, more readable. So there are justification for the truth of the proposition. Okay. And the scope condition. So the answer to the other question, you have to remember when, where, and whom. But the thing that is actually relevant is more thinking also about the actual context, the thing that characterizes the context of my theory. For example, for this theory is supposed to be applicable for distributed projects in which the operation are creation and modification of embedded safety critical system based on legacy code or new code. So quite a wide range of systems, but clearly here it refers to embedded systems. Okay, so this theory, for example, is applicable for software that goes in a car or in a train or in an aircraft, but is not applicable, or at least it was not verified in a context of financial systems or systems that for the public administration. Okay. Okay, in this example, this is an important thing to consider. I am answering all the questions. Okay. But most of the time you leave out why very frequently. Okay, so a theory in principle should answer all these questions. Okay, but very often the explanatory power, so the way a theory is able to explain why is very frequently quite weak. And you often need more studies for developing an answer to how and an answer to why. Okay. So this is for the elements. Then we want to understand how theories are formed. There are several strategies, okay, for forming theories, and you will see that our method, the method that we will study, are applying one or more of these strategies. Okay. So first strategy is induction. Okay, I take an observation, I observe the reality, and I infer a generalized conclusion from particular instances. So take an observation of a set of developers, and I start developing the theory. So I identify first the constructs, then the proposition, the explanation, and the scope. Okay, and the context. From the theory, I can deduce some hypotheses. I can define some possible hypotheses that will be derived directly by my proposition. Okay, and then I have to attest the hypothesis. So this is the second step, that is deduction. And deduction means taking the proposition of the theory, derive testable hypothesis. You will see testable hypothesis in the next lecture, like a large set of examples. And then you have to verify that actually these hypotheses are true by observing the reality. So you compare the hypothesis against the reality. When you have built the theory through this iteration, okay, so you have inducted and you have elicited some information and you have deduced testable hypothesis for the theory, then you may want to extend the theory to other fields. For example, you've developed the theory for the one that I was showing before for embedded system, and you may infer that that theory may be applicable also in the context of public administration system. Then I deduce new hypotheses and I test them in the public administration system. So this is the way the cycle works. So I start normally from induction, but very frequently there is already some theory around, so some information around. So some preposition that I need to verify. From this, I deduce hypotheses. I test them in my environment, and when I have some solid theories or referred to similar context, I can abduct. So I can use the method of abduction and take create, let's say, a more general theory and port it to another context. Okay, port it to another context and derive new hypotheses and perform a new test and observation. Okay, yeah, and derive new testable hypotheses for a theory also through the second step of deduction. So remember this: induction comes from observation to theory, deduction comes from theory to hypothesis, and abduction go from theory to theory. Okay. How do I evaluate the theory? Once I've developed my theory, how can I evaluate it? Here are 6 criteria for evaluating it. Okay. First of all, testability. So a theory is somehow scientific if it is built in such a way that it can be falsified. Okay, it can be tested. It can be tested. We will see this falsification concept later on. Here, I wanted to leave it. I wanted not to focus on it because it's more related to the way we test quantitative theory. But in any case, testability is a theory that can be put against reality, and we can do some empirical refutation. Okay. Empirical support. How many studies are supporting it? How much information from empirical studies are actually supporting my theory? Then I have explanatory power, that is to which extent my theory explains why. Okay, explain why question. So have I considered all the possible motivation that may have led to this conclusion, or am I losing something? So for example, in the example before, in which I have the list of reason why UML makes documentation better. I may have missed some other variables that might have influenced my outcome, and so there may be different reasons with respect to the one that I found for explaining my theory. Okay, parsimony. So how much effort did I make to minimize the number of constructs involved, and also preposition. Generality. So how large is the scope of material? How many contexts am I covering with this theory? And utility. Utility is very important for our domain, because the knowledge that I acquire through the empirical software engineering research, it needs to be useful. Okay, it needs to have, to a certain extent, some applicability. So as it was shown in the first lecture, the path is always arriving to a solution theory, to a theory that is oriented to transform the reality. Okay, this is a peculiarity of software engineering theories. Okay, to consider how useful can they be. It is always not always easy to say, okay, this theory is useful and this is not, but it is important to reflect and to make some arguments why it could be useful. Okay, because it is true that science and many things that we develop through research, their utility may not be self-evident. Okay, but in software engineering research, you have to argue, since it's not fundamental research, it's research related to company, to the way people behave, to code, into something very, very concrete, very, very practical. Utility is very relevant. Okay. So how do I formulate theories? This is a step-to-step guide. Of course, as you may have known from your experience as software developers, thing never works step by step, of course. But to somehow communicate them, we need to pretend that they are working step by step. Okay, so first of all, we need to define the construct of the theory. So which are the building blocks? This can be novel constructs or existing ones, so taking from existing theories that I want to take as a reference, or they can be refinements of existing ones. So I take constructs from other theories, from other research, from other literature, and I refine them. Okay. So, for example, in the case UML development methods, I may want, taking that theory, I may want to consider only one type of diagram, the class diagrams. Okay, to which extent the class diagrams, for example, help in improving documentation. Okay, this can be a way of taking a theory and trying to build on that by refining the construct. Or I can use novel constructs that are somehow related to the previous one. For example, another type of diagram, another type of development style. So this is to tell you that every time you build a theory, you may take also subconsciously inspiration from some theory that already exists. It is good that you make it explicit when you define the theory. What are the drivers and what are the sources from which you are taking your constructs? Okay. Then you define proposition. Again, they can be novel, they can be modification or refinements of the existing ones, and basically they connect our constructs that are relationship. Then I can provide explanation to justify the theory, so a series of assumptions and logical justification. And this explanation, they can refer to existing theories, and they can come also from other disciplines. So the possible explanation. So again, an explanation is related to a construct. Okay, there is a motivation that explain a relationship between constructs. Okay, and it is represented here. The explanation is the source of this relation is this other construct. Is this this other element? Okay. And finally, define the scope of interest. Okay, the fourth element that are the values of the constructs and their combination that the theory is oriented to explain. Okay, we will see that there is a difference between the scope of interest and the scope of validity. But here we are interested in what we are oriented to explain with our theory. Remember that every time, you apply an empirical method, you are actually building theory. So your goal is always to build a theory with the different flavors, so descriptive, explanatory, predictive, but still you're building theory. After I've built this theory, I need to test it. Okay, otherwise there's no empiricism. Okay. I have to evaluate how valid is this theory, and the steps are this one. I have to research. I have to select a research setting and a sample. By sample here, I mean not just actors, but activities, systems. So all the things, all the components that I can use in reality to identify my constructs and to test my theory. Okay, research setting here, it can be like, for example, a company, or it can be a laboratory. Okay, we will see in the different examples of research types, in research strategies, that different settings are possible, more natural or more contrived, so more artificial. Like a lab is an artificial setting, a company is a more natural setting. Okay, then I operationalize theoretical construct into empirical variables. So I transform these constructs in variables that they can be measured in reality. So a term like testability or documentation quality needs to be measured. Okay, and then I translate this into theoretical the theoretical propositions, so the propositions that belong to the theory, into hypotheses, as I was saying before. So I transform this proposition in hypothesis that I can test. The hypotheses are expressed in terms of empirical variables. And this is typical of qualitative studies, okay? But the philosophy is very similar also for quantitative studies. So is something that that you have to consider for any type of theory, okay? And then I have to test the hypothesis. So I have to verify that this hypothesis actually holds for my context, okay? And when we speak about hypothesis testing, is always we always refer to quantitative statistical tests. But as I was saying before, this process applies to both quantitative and qualitative method, although the terminology is like empirical variable, empirical testable hypothesis, and testing the hypothesis are really mostly for quantitative studies and experiments especially, okay? And finally, define the scope of validity, okay? I have selected a sample, and therefore I didn't verify my theory for the whole possible set of samples, but just for a specific set of cases, okay? Scope of validity is the part of the scope of interest in which the theory has actually been validated, okay? So here is a summary in terms of a graphical summary of how the theory is built according to the steps that I gave you before. So first of all, the constructs, the propositions, explanation, and then the scope of interest, okay? Then, given this is the theory from which I start. I operationalize the variables, and I transform and I identify my hypotheses that are basically the representation of the proposition in terms of the concrete variables, okay? And I identify the sample. You already see that this sample is smaller than the context of the theory, okay? And then I'm still somehow in an abstract space, but closer to reality. The final step is data collection and measurements, in which I actually go to the reality and collect this data. Once I have defined the sample, I can apply the sampling strategy, and I can identify all my data with the different data collection techniques that I explained you last time. At this point, at this point, I can, having my data, I can test whether my hypothesis holds. So given my data, I check, hey, is this hypothesis true or not? I can confirm and reject the hypothesis, and therefore support or not support my theory. And I can identify my scope of validity. So after I have verified in a certain specific context, and I have identified the scope of validity, I can say, okay, my theory holds for this specific context. The scope of validity here, you have an interesting image that tells you that to cover the scope of interest of a theory, you need multiple studies that may cover different scope of validity, okay? So here you have a scope of validity for study 1, for study 2, study 3, and all together they cover a part of the possible scope of interest of the theory, okay? Threats to validity. This is another important point that you will encounter in every method, okay? The fact that you've done all this very nice process of starting from the theory and empirical verification, etc., doesn't mean that your theory is accepted or rejected, okay? You need to provide arguments that you didn't do any mistake, okay? And you need to provide arguments that you didn't do, especially invalid operationalization of theoretical constructs and propositions. So, for example, you need to justify the fact that a construct such as the complexity of the code is represented with line of codes. Is it a valid operationalization or not? You need to provide arguments, okay? To which extent this operationalization is valid. Or inappropriate research design. So you may have selected the wrong sample, you may have made mistake in the data collection procedures, in the data analysis procedures. So you may have made mistakes across the step, and you need to demonstrate that you didn't do that. Inaccuracy in data correction and data analysis. This is related, of course, to inappropriate research design, and possible misinterpretation of the empirical findings. So what you found was actually clearly linked with the data, and you didn't do any wrong interpretation. In general, each research method has its own classification. Those that I listed before were some intuitions behind the concept of threats to validity. So anything that you could have done wrong in this process, okay? But then in each type of research method, you use a different classification because you may have different types of threats, different type of mistakes that you have made. And this is a general classification that is typical for experiments, but it's useful to remember, okay? Because it gives you the flavor of what are the main concern in threats to validity evaluation. First of all, construct validity. That is related to the question that I was explaining before. Have I operationalized all the constructs correctly? So my constructs are actually represented in a proper way by my variables. This is the question, okay? And you have to provide sufficient arguments. Internal validity. Are there any aspects that may have influenced my outcome and I did not consider? This is related mostly to your design and data collection method. Okay, and in this case, you have to identify which are the possible variables that you didn't control and you didn't consider, and that may have had an impact on your design. For example, if I am evaluating the complexity of a code and I'm using some code samples, okay, and I want to let actual people assess the degree of complexity of this code. I have to be sure that these people did not already see the code that they are evaluating, because otherwise the evaluation of complexity is biased. Okay, if you all know already, if you've seen already a certain code, of course it will be less complex than for another person who didn't see it, who never saw it. Okay. These are typical internal threats. So other variable that you did not consider in your experiment or in your study, and that have an influence on your outcome. External validity, that is related to which extent are my findings generalizable. So this is related to how much my scope of validity basically covers my scope of interest, or how many contexts can I cover. Okay, which, for example, which type of languages are considered here in this example? Complexity, yes, but may be different from if I'm covering C code and Python code. So if my experiment is made on both C code and Python code, then I have quite a good external validity. But if it's just made on one type of code, it's more limited. Okay, these are three that are quite clear and I think quite intuitive as type of threats. Okay, this we saw in the example before. Let's make a step back. In the example before, we saw this. We saw that we were passing from theory to reality. Okay, this was the typical process for a deductive approach. If you remember the early slides, because I'm starting from theory. I assume that I've built the theory somehow, and I go towards reality. But the reality could be also that I don't have a theory yet. So I need to start from observation. I need to start from the the reality. And in this case, I use the so-called inductive approach. So the one that I showed before is the typical, if you want, positivist approach for constructing theory. So the deductive one, you start from some constructs from the literature, from propositions, and you create hypotheses and then you test. But in our diagram, we saw also the inductive process. Okay, we will not cover here abductive processes, but inductive is important because it's typical of the so-called constructivist approaches that are the ones used in qualitative studies. So in this case, I start from sample definition and data collection. For example, I collect some interviews in a company, and then from these interviews, I identify which are the constructs. Okay. Then so the basic thing is that I start from my sample definition, and then afterwards I identify variables and propositions. Okay, and from this I can build my theory. So the theory comes afterwards. I am eliciting the theory from the data. Okay. I can combine the two approaches, of course, because in a case in which I don't know much about a certain reality, like the reality of a specific company, and I have to start with a collection of interviews before knowing what is actually relevant, what are, for example, in the example before, what are the elements that may affect or in which way the UML language can affect the development, to understand the ways I have to ask to people to understand that, for example, it affects documentation, it affects the stability or other aspects. Okay, then I have built the theory in an inductive way, but afterwards I have to test the theory, and I can apply a deductive approach. Okay, I can take my proposition, I can operationalize into more refined variables, for example, into more measurable variables, so give a way of evaluating the quality of documentation. Then I do, again, a round of sample definition and data collection, and in this case, I do my hypothesis testing. So I deduce my hypothesis, I test hypothesis, and then I can refute or confirm the theory. So inductive process and deductive process are combined and are different steps of the theory constructions, and they are used at different stages. Okay, in one case, I use the inductive processes if I don't know anything about a context, and I use a deductive process if I already have some theory, or I can build some theory from the information that I have already collected. This remembers us when we were speaking about the different research questions. Okay, because theories are built and are guided in a hidden way here in this presentation also by research questions. Okay, when we were speaking about the research question, we were speaking about exploratory, explanatory, so different type of questions depending on how much information do I have about a certain context. And this is strictly related to this diagram. First of all, I will have exploratory research questions, and I tend to induct. I will tend to use a research approach that is more inductive. Once I have the theory, I will go towards more explanatory or more predictive research questions, and I will tend to use deductive approach. Okay. Now I'll give you an example. In here I was hiding the example between the lines, but this is the example basically. This is taken from the paper that I used as a reference here for building this lecture, and I invite you also to read the paper because, of course, it contains much more information than the one that I could give here. Here, the example is concerned with a field study. So a study in a company, basically, to investigate benefits and challenges of the use of UML in a large distributed development process, so a development project. So you have large and distributed, it means that you have different people working in different areas. So for example, one is in Milan, one is in Florence, or even one in India and one in Italy. Okay, so different teams belonging to the organization but located in different geographical locations. And you want to understand whether this UML works fine or not. So what are the benefits and the challenges? And the project was concerned, the project that they were developing is concerned with the safety critical process control system. Okay, you don't. This is needed just to identify the scope later on. In this case, you have 4 sites in 3 countries, so not just Milan and Florence, but other countries, for example, in Germany and in France. And you have many people, 230, and 100 of them are using actually UML. Okay, so they could collect information from individual interviews, questionnaires, and project documents. So the data collection was using different strategies. Okay, both interviews, questionnaires, so surveys, and also document analysis. Okay, also taking the documentation. So you see already the data collection strategies that I explained you before, they come handy. You have here some people intensive data collection methods like interviews, and some system intensive or object intensive like project documents. Okay. First, I define the constructs, and to do that, I perform a series of interviews. Okay, and from this interview that I performed with the people in the company, I identify which are the most significant concepts. Okay, how do I do that? You will learn this when we do qualitative study, and basically it's a strategy called open coding. That means labeling the concepts in the text, finding representation, finding fragments in the text that represent my concepts. Okay, so if people, for example, like in a trivial case, they mention that documentation many times, documentation may be relevant, and so this is one of my constructs. Okay, and I can find it during the interviews. Okay, they are speaking about documentation, and so this is a relevant construct. These are the examples, the same that I gave you before. So UML-based development methods is a construct because we are speaking about that. Cost, communication, design, documentation. So these are all the building blocks that I want to consider in my theory, and that are elicited, they are identified in the interview transcripts, okay, in the interview with the people. People are speaking about these things, so they are elements that I need to consider in my theory. Propositions. Propositions still from these interviews, I can identify not just the elements, but also the relationship. Again, the paradigm of entity relationship diagrams is still relevant here. Like you have identified the entities, and now still in the interviews, you identify the relationship. And these are translated into propositions, okay? Now I have a series of relationships. For example, UML affects cost, so increases costs. And I want to understand whether these propositions that I gathered from the interview are actually true for all the people, because the interview, some people may mention this aspect and some people may not. So I need to test this with questionnaires, this proposition, to make them more solid. Okay. Then I provide explanation. I see that in the interview there is some explanation that explains the reason behind the proposition, okay? And but in some cases, for example, I may have no explanation, so I perform further interviews that are more focused on finding explanation for certain statements of the people, and that allow me to list the explanation. For example, here I have the documentation is more complete, more consistent, more readable, because it makes it easier to find specific information to a common format, more understandable for non-technical people. So if I have the diagram, it is more understandable because technical people find it easier to understand the diagram than the technical written, the technical text. Okay, and maybe viewed from different perspective because I have different types of diagrams. So these are all motivations that I can find in the interviews. So we are at the step 3 now. Step 4, define the scope of interest of the theory. So with this theory, in principle, what do I want to cover? Okay, I started from a specific company, large company. My aspiration is that I want this theory to hold in a larger, broader scope. Okay, that is the scope of interest of my theory. The scope of interest in general in software engineering can be defined according to these 4 elements. One is the technology that I'm considering, and it is UML in this case. The actors that are involved, and here are designers in distributed teams. So these characterize my actors. Software system, here the type of software system is embedded software, large size embedded software. And activity is, in this case, create and modify UML diagram. So it's the editing of, I could also have called activity task, for example. A task that I'm doing is designing, okay, software design. Finally, I need to test the theory. So I've done all this interview, all this step in an inductive way, because I was following an inductive process, starting from the data of the interviews and eliciting proposition and theory. But then now I have the theory, but this theory is not fully robust, let's say, because I need to prove it. Okay, it's not proved. I need to verify it. Okay. And in this case, I apply a deductive step. The deductive step means that I take the single proposition or a subset, because probably to verify with quantitative methods, a deductive approach, I cannot consider all the proposition altogether, but better to focus on one at a time, and translate into hypothesis and do some study. Okay, for example, I can use I can take the proposition use of UML methods increases costs, and I can decide to assess whether this preposition that can be translated into an hypothesis is true by using different methods. For example, I can do a field study. Sorry for the typo here, but it's field study. An experiment or a survey. For example, if I do a field study, I can identify companies that want to introduce UML and establish a clear way to evaluate the cost. So I say, okay, man-hour is my way of evaluate cost. I consider another comparable company that's not using UML, and I check the resulting cost of the 2 companies. So here I am studying in the real world someone that is introducing UML and someone that is not, and I compare the cost. If the one that is introducing UML is having higher costs, then I can say that it is true. It is at least it is not false that the use of UML methods increases costs. Okay, then I can choose to do an experiment, for example. An experiment still related to the same proposition. In this case, I take 2 groups of subjects. I give them a requirements document written in natural language, so that explain basically what the system should do. I ask group 1 to take the document and write down the code, and group 2 to write the diagram and then implement the code. And then I can evaluate and compare the cost. Okay. In this case, I'm performing an experiment, very narrow, take group of subjects in a lab environment with a very well-defined requirement document. I have constraints in terms of time. It does not scale to. It does not consider the whole context of a company, but still, it's another way to evaluate whether this proposition is valid, to assess my hypothesis. Or I can do a survey, a questionnaire. So with the same statement, I can contact multiple companies that have introduced UML, and I can ask them the same questions, that I can ask them to state their agreement with my proposition. In this case, I can reach more people, and I can have an answer to more than one of these questions. But of course, I cannot go too deep into the reasons. For example, why someone is choosing a certain answer or not. We will see also this survey, and we will see all this type of study in our class. So based on the selected study, then I identify the scope of validity that is larger for survey and narrower for field study. As I was saying, if I am using a survey, I'm reaching many more people than if I do a field study. So a field study is proving somehow, is verifying the hypothesis, is testing the hypothesis in a more restricted context. Okay, but if I do a survey, I am verifying, I'm testing my hypothesis in a much broader, much larger context. Okay. Then, still in this example, as I said before, there are these different ways of evaluating a theory. In this case, I assume that I didn't do the theory testing. So I stopped with the inductive stage. So the testability is that in this case is average, is not so high, because it is true that constructs are well defined and the propositions are clear. But on the other hand, these are definitions, these are not numerical, and the data collection was qualitative. So I've done some open coding, so I have used strategies that are somewhat subjective. So testability is limited, and I could have different results. Okay. Empirical support seems to be good, because, for example, I find other studies that seem to support my proposition. Explanatory power is also limited, because motivations are derived from the interviews. So the reasons why have not been actually, I didn't consider all the possible variables that may explain why. Okay. Parsimony, I can give arguments that the number of constructs is limited. The generality is a bit limited, because my scope is related only to a field study in a specific company. Okay, but the utility is very high, because it can help decision making. So if I am a company, I know that this very large company has used UML, and it has affected the cost, but it has improved the quality of documentation. I can know what to do. If I have money to invest, and I know that in the long term using this language pays off, and this is written in a paper from a study of a large size company that is comparable to mine, this is extremely useful. Okay, I don't have to take, I can take the risk of introducing UML. So this theory may be not so much supported, not so much general, but still very useful. Okay, and these are all arguments that when you develop a theory, when you do an empirical study like the one exemplified, are all logical arguments that have to be checked by peers. So you write these arguments, these are just words, but the so-called reviewers of your research will check whether these arguments are sound. Okay, so there is a research community, a set of other people that will read your arguments to support your theory, and will be allowed to evaluate your work. Okay.